then I'll start. I'll start straight from the end and then sort of go to the beginning and work my way back. So let's first sort of state the result somewhat more informally. I'll sort of add more detail later. So let's first use these lowercase letters like D, E, F, and so on to range over sort of what's in the chief theoretic framework are called empirical models, but you can think of things like PR box or the correlation state or other sort of correlations you can get, whether quantum or not, or contextual or not. And then we write a tensor symbol if we have two sort of systems like this side by side running independently. So there's sort of no correlations between them. And then we write this squiggly symbol, a squiggly arrow, to denote that there is a transformation that takes D and builds E out of it in a sort of resource theory of contextuality, which means that we have some kind of intra-conversion with these correlations, and that's sort of the convertibility preorder of this resource theory. I'll make all of these more precise later, but now with these symbols, we can already state what the result is saying. So we're basically saying that there are no catalysts in this resource theory. So more precisely, we're saying that if from a product of D with something else, you can simulate D and F, then there already was a transformation from E to F. And the reason why this rules out catalysts is, well, let's first recall what a catalyst is. That would be a state D such that there is no transformation from E to F, but when you add in the catalyst, you can do this transformation and get D back. And now, because this theorem says that whenever you have a transformation like this, then there already was a transformation before this, then this sort of putative catalyst D didn't really make the transformation possible because it already was possible. And the same holds for the resource theory of non-locality. I'll talk later what the relationship between these two are. And one of the reasons why I think this kind of result is interesting is because it actually shows that sort of, I mean, it's one further way in which contextuality and non-locality behave differently than entanglement. So we often think that entanglement behaves sort of similarly as a resource theory as non-locality, although there are already known results called anomalies of entanglement that show that in some situations they behave differently. And this is one further case. So if you think of entanglement as a resource theory where your states are quantum states and your conversions are local operations and classical communication, or maybe stochastic such, then it's famously known that there are catalysts. So there are situations where you can't transform a quantum state to another one, but if you add in a catalyst, then suddenly you can. And this is false for non-locality and contextuality. So let's next discuss, again, still in a nutshell, how do we make this slightly more precise? So I'd like to say that the sort of resource theory of contextuality is not something that I sort of develop in this work. I just take it from earlier work with Samson and Rui and Shane. And this, even though, I mean, the paper, well, it's sort of written for sort of people in logic in computer science. So it might look very alien to sort of people working in a more physics background, but I still like to think that it just is a very sort of careful mathematical formalization of the already known and widely used paradigm of sort of how can one transform correlations to others. So there's lots of prior literature in the non-locality literature where people ask whether you can sort of wire these systems together and maybe use some shared randomness or priority input classical communication to transform some resources to others. The reason why I just want to work in some particular framework is to sort of have enough mathematical structure to make the problem tractable. So I chose the framework I'm most familiar with. But I do believe that this result is a fact about the general paradigm itself, and it's not just an artifact of sort of the way we choose to formalize this. How about non-locality? Well, I'd like to think that, I'll elaborate on more on this later, but I'd like to think that that's closely related, but not exactly the same resource theory. I'd like to think that there is a general way of taking any resource theory whatsoever and building a new resource theory of n-partite resources of that kind and n-partite transformations between them. And I'd like to think that n-partite non-locality is sort of the resource theory, what you get when you start from contextuality in this sense and do that same general construction. And finally, in this overview part, I'll give a brief gist of how the proof, roughly speaking, goes. So the idea is that if you can use D to transform E to F once, then because the catalyst doesn't get spent in the process, you can do it as many times as you wish. And if you then reason carefully what happens when you're doing this catalyst operation a very large amount of times, it will imply that you only need a compatible part of D, or rather a compatible part of measurement protocols over D. And because all of this fits into a single context, that part is automatically non-contextual. So you can then replace the whole thing D with something non-contextual and still get the transformation, which then implies that you didn't really need D. This was already possible in this resource theory. So now let's move on. And this is, I think, a slide that already was in the earlier talks before the break. So I'll go through this a bit faster. So the way we formalize, first of all, our sort of basic object is that we start from having this notion of a scenario where you have a finite set of measurements, and then you specify which measurements are jointly compatible. And then you have an outcome set for each measurement. In principle, they could all be the same, but for some technical reasons, it's sort of handy to keep at least the possibility that they differ for each measurement in X. So for example, a standard example of such a scenario would be the case where you have Alice and Bob. Both of them have two measurements. So Alice has measurements 0 and 1, Bob has measurements 0 and 1. And then the compatible measurements are given by saying that, okay, Alice can choose one measurement, Bob can choose one measurement. And those are always compatible. And then, of course, any subset of those. And then an empirical model on such a scenario is given by saying, okay, for each joint measurement that's possible, list the sort of marginal distribution you see when you run that measurement. And furthermore, we expect that these sort of satisfy this no signaling condition. So if you measure only sort of some set of measurements, it doesn't matter what else you're measuring with it, the sort of marginal distribution for those measurements doesn't depend on what else is being measured. And that sort of generalizes this no signaling idea. And in this bipartite case, it's exactly the no signaling condition. And again, in this framework, contextuality is just a, non-contextuality is the fact, corresponds to the fact that there is a joint distribution on all measurements at once that explains the sort of marginal distributions we're seeing. And now if there isn't such a global distribution, then we'd say that the system or the empirical model is contextual. And that corresponds to sort of this idea that the system is locally consistent. So in each context, so in each measurement, possible joint measurement, we get a well-defined classical probability distribution, but somehow we can't glue all of these together at once. And now the reason why we're of course interested in this is that this is something that arises in quantum mechanics and potentially ties to things like speed ups in quantum information and computation and stuff like that. So now let's move on to discussing how we transform these systems to others. And this is something I've sort of talked about earlier in QCQMB 2 years ago. So I won't focus as much on that, but I want to still remind the listeners what we were doing. So let's first start from a sort of simple way of transforming one scenario to another. So here we're depicting a transformation of the sort of scenario S to the scenario T. And the idea, the picture to have in mind is that you actually have just a box of this type, a system of type S, but you want to pretend that you have a system of type T. And now in the simplest case, everything is deterministic and single valued. And the way it works then is that you say, okay, whenever someone tells you to measure something in T, so in the box that you pretend you have, you actually translate it by some function that tells you what to measure in S instead. So then, okay, someone asks you a question about T, you measure a corresponding question in S. So you run S, you get some answers, and then there's some rule, some function that tells you what outcomes in T you pretend you got. And any such sort of recipe is then a map between these scenarios. So more formally, you'd say you have two things when you have a map from S to T, so a way of building T out of S. You have a function from measurements of X to measurements of S. And it should be a simplicial function, meaning that it preserves compatibility of measurements. So whenever you were asking a compatible set of questions in T, you end up interpreting it as a compatible set of questions in S. And then you should have a function that tells you whenever you get an outcome for some measurement in S, how do you interpret it as an outcome of a measurement in T? So sort of a way of post-processing these outcomes. And now this is just the transformations of these scenarios. Well, how do they relate to transformations of these empirical models over these scenarios? Well, if you had some data in this picture, you had some system in E over S, then when you run such a procedure, you get some probability distribution or some empirical model over T. And then we'd say that this procedure simulates you having some empirical model over T exactly if this process of taking the system E in S and transforming it according to these rules gives you the target 1 over T. So this is something one could write in terms of equations, and it is indeed done so in our papers on this stuff. But instead, I'll draw a picture about this because this will help me later when we sort of slightly switch the viewpoint. So now, compared to the previous picture, we're thinking of this a bit differently. So we think of this D as an empirical model over some scenario. And now there's only one wire coming up. So we think of that wire as sort of an interface where you can interact with the box. So you can both ask questions at it and get answers back. So it's sort of bidirectional. And the reason why we only draw one wire is that we sort of abstracted it's just whatever type, and you can only ask the kinds of questions that D lets you ask about this. And then when we plug F after it, that sort of means that we sort of interact with D only via this interpretation that F gave us. So when we ask some question about T, then F tells us what question to ask about D. And then we get some answer in D, and then F transforms the answers back into answers of the correct type in E. And we'd say that this map F then is a deterministic simulation from D to E, precisely if when you do this transformation to D, you get exactly E out of it. So here's one example of what you can do with this. So if you think of PR box that we had in an earlier slide, that's a system on a square. Well, you could also think of what sort of the Specker's parable of the seer on a triangle. So you have 3 measurements, any 2 of which are possible to measure, but you can't measure all at once. Well, you can imagine a sort of flyer kind of system on that. And turns out that that's powerful enough to simulate the PR box. And the way it works is that sort of you think of the vertices of the PR box. Well, 3 of them you map to just vertices of the triangle, and then one edge you collapse into one point of the triangle as well. And then you need to take care of what you do with the outcomes so that you get exactly the correct answers. But anyway, so in this way, you could simulate PR box from a triangle. Now, this is the simplest sort of setup, but we actually need to build some more complexity into the notion to get a more realistic and useful resource theory of to capture the kinds of simulations people already used in the physics literature. So first of all, you might want to allow a measurement in T to depend on something more complicated than just a single measurement in S. You might say, oh, but I want to measure these 5 things at once and then get the outcome. Or you might want to do some more complicated measurement protocol where you say, oh, I want to first measure this. Then based on the outcome, I choose what to measure next. And then based on that outcome, I choose what to measure next, and so forth. And the other aspect you might want to do is that you might want to use classical randomness. So for example, you might want to choose randomly what to measure in T, and then when you get some outcome, you might want to randomly then choose what outcome it means in S. And the key part of this is sort of this measurement protocol construction that's done in earlier work. So what it does is it takes one of these scenarios and then builds this new larger scenario of all measurement protocols over S, where the new measurements of this new larger system are measurement protocols over the original thing. And here, deterministic measurement protocol is something that you can either think of the empty measurement protocol, which is finished, or then you have something more complicated, which measures something in X, and then based on the outcome, chooses what measurement protocol to do in the remaining part of the box, where the remaining part of the box is given by the link of X. So that means all the measurements that are still compatible with this measurement X that you already did. And then an outcome of such a measurement protocol is given by an outcome for each measurement you did during this measurement protocol. And finally, you'd also need to tell when can they be combined. And informally, the idea is that a set of measurement protocols is jointly compatible if whenever you sort of run them in parallel, you'll only end up asking compatible questions from the system S. And this actually turns out to be equivalent to the fact that you can just combine them into a single measurement protocol that gives an answer to all of the measurement protocols at once. So now, with this defined, you can then say that adaptive simulation or map of systems is something like this. So instead of mapping measurements in T to measurements in S, you map them into measurement protocols over S. So to measurements of MP of S, and then you run S, and you still get some well-defined outcomes over these measurement protocols. And then you have some rule that tells you how to interpret these outcomes in T. And now to get classical randomness, you just say, oh yeah, you can augment the system so you're allowed to use an additional box as help, as long as this additional box is non-contextual. So this is kind of the local operations and shared randomness paradigm. So the shared randomness now is given by this box C, and the requirement is that it should be classical. So then you'd say that, okay, in the sort of more general sense, a simulation from D to E is then a deterministic simulation from the measurement protocol operation applied to D times C for some non-contextual model E. And now the earlier theory we've done guarantees that these compose. And now the C lets us use classical randomness. And then we use the symbol now to say that, okay, a map like this exists. Then we just write that there's a map squiggly arrow from D to E, and we'd read it as saying D simulates E. And now in earlier work, we've sort of tried to justify why this is a reasonable notion. So first of all, I think it captures the kinds of simulations people already used in the literature. at least when you restrict to exact transformations of correlation. So if people do stuff like distillation, then they ask what happens asymptotically in the limit. You can probably adapt this framework for that, but so far it hasn't been done. Now, if you want to do everything super precisely, it's a bit of a headache, but in any case, in principle, you can do it and write everything down formally if you want to. And this behaves well with these other measures. So for example, contextual fraction is a monotone for this notion of a simulation. And you can express contextuality as saying that you cannot be simulated from a trivial model. And there's versions of this theorem also for logical contextuality and strong contextuality. And now let's move on to discussing how this proof would go. So the first step is that we start from the definitions, and then we reduce to the fact that we get a deterministic simulation. So again, I should have MP in the codomain here. Maybe I'll fix it in the slides later, or you could think that we work in the sort of co-classic category of this if you know what that means. But anyway, if there is a sort of simulation from D to E to D times F, then there's a simulation that's deterministic, where we use some classical randomness C as sort of giving us the classical randomness. And now if we combine the classical randomness into this model E, then we have our ordinary deterministic simulation still from the MP of this thing to D times F. And now, if you can catalyze once, you can do so as many times as you wish. So you can first do this catalyst process and transform one copy of the first copy of G to the first copy of F. Then you transform the second copy of G to the second copy of F, and so forth. And now there's a bit of work to deduce it from here, but you can then conclude that you can end up in a situation where for any n, you have a simulation like this, where when you're simulating the ith copy of F, all the different simulations of different copies of F do the exact same thing on D, but they all use different copies of G in the process, but otherwise they do exactly the same. And now let's see how this sort of lets us conclude that we only need a compatible part of D. So part of this definition of something being a map of scenarios or a simulation is that we have a simplicial map, which means that compatible questions get transformed to compatible questions. So in that case, in our case, it means that whenever you're asking questions of different copies of G, then they get translated into different, compatible questions. When you're asking questions about different copies of F, they're compatible, so they get translated into compatible questions here, which in particular means that anything they ask about D is compatible. And now if you choose n that's large enough to exhaust all the different possibilities of what kind of behavior you could get in D, the upshot is that sort of all of these have to be jointly compatible. So you can join all of those into a single measurement protocol over D. And then you can build a new simulation where you just simulate the first one copy of F, where you first measure this single massive measurement protocol over MP of D. And then because that asks all the questions you might ever need to ask about D, you can then move on to G and never return back. And now this describes a deterministic simulation like this, where D has only a single measurement, which represents the whole complicated measurement protocol over D. And whenever you have a system with only one measurement defined on it, that's automatically non-contextual. So we've sort of transformed this supposed catalyst D into something that a system with only a single measurement, and hence something that's automatically non-contextual. And now I don't have much left. I'll explain briefly how this transforms to the n-partite version. So I'd like to think of it as a sort of n-partite version of the theory. So you'd say that a resource is a system or empirical model defined over an n-partite scenario. And a simulation is a simulation like in the previous case, except you should give a simulation for each of the n parties. So in pictures, it looks a bit like this. So the idea is that if, I don't know, Alice, Bob, and Charlie share some box, then when they want to transform it to E, then Alice should only do measurements on her part of her system, and Bob, similarly for Bob and similarly for Charlie. And of course, you might still want them to share shared randomness. So then you say that, okay, you can also share an n-partite box, and then you can only use sort of your part of the shared box and of the box D, that's your resource. And if you slightly modify the proof before, the result is that it still preserves this property of the simulation being n-partite. It doesn't quite work with the argument I just outlined, but in the paper, I give a version for which this comes up automatically. And you can actually work this out even slightly more generally. So here we had always a sort of requirement that the shared resource that you can use for randomness is non-contextual, but actually you could take any class of models that as long as it contains all non-contextual models and is closed under tensor product, and then you could just declare those to be your resources and get the notion of X-assisted simulation. So you could think of, for example, quantum-assisted simulations. And the upshot is that the theorem still goes through pretty much with the same proof. And concretely, what that would mean that even if we allow us to use quantum correlations, if aliens show up from outer space and give us a PR box, we still can't use it to get the transformation done without actually using it. So if we try to use it as a catalyst so that it doesn't get spent, then we can't do anything that we couldn't already do. And that's it. Thanks. Do we have any questions if there's time? Yeah, go ahead.
Well, I mean, just picking up your last point. So obviously we know there, I mean, so the key point is that the catalyst is you still have it at the end, just as you did at the beginning.
Exactly. Exactly. Yeah.
So, because of course we know many sort of examples of right.
Yeah. So indeed. So if you have a PR box, you can do all kinds of wonderful, magnificent things. The point is just that this sort of theorem sort of says that they do get used in the process. So if you just wanted to use it as a catalyst to sort of and not spend it on the way, then you can't do anything that you couldn't already do.
Yeah. I mean, I'm just wondering if there could be a sort of quantitative version where you sort of, let's say with respect to the contextual fraction or some other measure that you can sort of spend, I mean, you're sort of quantifying how much contextuality you need to spend in, I mean, maybe it, I don't know, I mean, but there could be something.
This is a very interesting question. So does this sort of, so this sort of suggests that contextuality is some kind of resource that you spend in the process. So can you actually sort of measure it rather than just give a sort of binary case like this? And sure, that's certainly an interesting future direction.